Thank you. So welcome to the seminar of the SoSE Astani Department of Civil and Environmental Engineering. Today our speaker is Dr. Joanne Lane. Let me tell you a bit about Joanne. She recently completed her PhD at USC from the Industrial System Engineering Department. And advisor were Professor Barry Boehm and Stan Settled. I don't know if you know these two individuals, but they're quite famous. Barry actually is the head of a DOD, or one of the PI, principal investigator of one of the DOE center on system engineering research. So area of Dr. Joanne is also system, but actually systems of systems. That means SOS. 3 long, 3 short, 3 long, if you know your Morse code. She was, as a PhD candidate, she was awarded the 2007 International Council on System Engineering. That's INCOSE, from the foundation, and she was also awarded the Stevens Doctoral Award for promising research in system engineering and integration. So she is now working on this DOD center, and she's going to tell us more about systems of systems. Joanne?
I'll figure it out.
Yeah, you can click one is short. You have a clip. You can put it, yes. That's a good way. Okay?
So we can get this on here. I'll just hold it. I can hold it. Okay, thank you very much for that introduction. Yes, my research area has been system of systems, and that was also the research area for my dissertation that I defended last January. And I was lucky enough to transition into the System Engineering Research Center to continue this research with funding from the Department of Defense. They're quite interested in it. And so as we talk about systems of systems today, it might sound a little bit more like DoD systems, but we've also been looking at systems of systems from other governments like cities and counties and states, as well as in the commercial arena. So what I'm going to do first is start out with some basic definitions. When you start talking about systems of systems, the first question that comes up is, what do you mean by that? And what do you mean by system of systems engineering? And so I'll set the stage a little bit, and then I'll go into some of the system of systems engineering strategies and areas that we've been doing a lot more research in, pushing on to understand what's going on and helping to improve processes in this area. Some of the key ones have to do with incremental commitment and development and evolution of these. They're big, they're huge, they're complex. You can't build them all in one big bang. How lean principles fit into what people are starting to do as they're trying to manage system of systems. Looking at cost estimation. As soon as you come up with an idea, the next question is always, how much is it going to cost us? And what do I need to do? So we've been working on that. When you start doing system of systems engineering and trying to manage it, what are the engineering artifacts that are produced that help communicate knowledge among the different teams and different stakeholders? And lastly, how do we test these things? And you'll see what some of these challenges are. So I'll go through these research areas to start with, and then as part of our work, we've been developing this conceptual model. We talk about Ensayo. If any of you know it, it's like the fictional city or county. We don't want to call it San Diego. We don't want to call it Los Angeles. We don't want to identify it because the politicians might get upset with some of the things that we say or that we're trying to demonstrate and those sorts of things. But well, I'll talk a little bit about this RACRS in Ensayo. And then I'll quickly go over how our research is continuing to evolve. And then lastly, some acknowledgements for all the people that have been giving us data and information to help with this research. So what is a system of systems? Well, Basically, it's whenever you integrate multiple systems together. When you start calling a systems of systems, though, usually somebody has thought about putting some sort of infrastructure or framework in place that you can kind of characterize and document and then start evolving, improving, and that sort of thing. So it's this huge framework or architecture that you're integrating what we call constituent systems. And these are systems that have typically been out there for a long time, operating on their own. Down here we have some of the characteristics of these that, as I said, independently developed and managed. That means that somebody else, some other organization, different organizations own different constituents. They have their own funding, they have their own stakeholders, their own evolutionary things that they're trying to do to help their stakeholders at the single system level. They can be new systems, relatively new. They can be old legacy systems that have been around for 20, 30, sometimes even more years. And they can be in different stages of development. We'll see how this asynchronous development comes into play and some of the challenges. In later years, there's been a lot of commercial off-the-shelf products developed that systems of systems are integrating. It might be relational database management systems. It might be the Esri GIS types of systems that they're using. All sorts of commercial products out there that are being integrated and becoming part of these. Global Positioning System is another one. While that's actually a DoD Department, an Air Force system, it's got commercial applications out there that we can integrate in. Each one of these constituents, in my definition and in Mark Mayer's definition, of systems of systems, has its own purpose. So it can operate on its own outside the system of systems, as well as participate in the system of systems. And this also leads to this other one is sometimes, and you'll see this in the RACRS, the Regional Area Crisis Management System, sometimes the systems operate on their own 90% of the time, and then when some event or trigger happens, then they come together to handle the situation, and when that's managed or handled, then they go back to their single system state. So a couple of, or two primary domains that we see with systems of systems. First is the military or crisis response one, and those are dynamic. You see these sorts of things happening every day over in Iraq and Afghanistan. It depends on what the mission is, what do I need, how many tanks, how many airplanes, how many drones or UAVs or unmanned ground vehicles to go in and find the IEDs. And so they configure a system of systems, link them together so that they can communicate for the mission. They go in, they do the mission, and then they come back, and then they go in, in standby mode waiting for the next mission to get called. In the business area, we talk more about the enterprise-wide types of systems and cross-enterprise integrations. An example of that might be a healthcare system in a hospital. Large hospitals are integrating the patient management records with radiology, with the lab, with the pharmacy system, the telemetry systems, and all those sorts of things, so that you have single point of entry of information about the patients, and that information can follow that patient department to department, and if that patient is admitted, everyone, all the service or healthcare providers can see that same information on that patient. And you'll see a lot in this enterprise-wide that there's a service-oriented architecture that's being used by a lot of organizations to pull together and integrate their systems. That's their actual framework. Feel free to jump in and ask questions anytime, but we're just kind of going through some of the basic definitions now. So as we started researching these systems of systems, we came up with this taxonomy to classify them. There's lots of taxonomies that you could use, but the one that we were really interested in is how are these organizationally, how are these systems of systems organized, and how are we going to be able to manage them? So this taxonomy is kind of based on levels of authority and responsibility. And depending on how much authority and how much responsibility you have, it kind of informs what you're going to be able to do from the management perspective. What management approaches are available? So the first level is little responsibility, little authority, maybe close to zero, and it's what we call the virtual systems of systems. And our classic example of this is the internet today. Basically, the only thing you kind of have guiding it is a standards group that will talk about, you know, whether it's IPv4 or IPv6 for the communications protocol. And what they said was, and this started out as a DARPA project before it went worldwide, is we're going to build this and people will come, kind of like the Field of Dreams, if you remember the football movie. So we built this internet, and over time, every business started jumping on and realizing that they had to have a presence on the internet in order to survive, whether it was intranets, extranets, wide area networks, or just out there as a business on the internet. As you can guess, you don't know who all the constituent systems are. You don't really know how to manage them. Each one of those systems is going to pull information that they need from other people on the intranet or internet and do what they need and set up collaborations for whatever their business need is at the moment, and then those connections go away, and later on they'll establish other ones. The next one coming up in the scale of responsibility and authority is what we call the collaborative. And in this case, there's a group of systems, and they pretty much know who they are. And they're given some needs, some capability needs that they need to implement as a collective. And they work together. They need to negotiate. It's more of a peer-to-peer type of negotiation to come together to figure out how to implement that capability across their systems. Key here is there is no system of systems engineering team or management structure in charge of them. It is truly a peer-to-peer type of collaboration. Going up the scale then is the acknowledged system of systems, where somebody typically has come along and said, you know, this group of systems, it's really important. And I just can't let it operate any longer as a collaborative one. I need to put in some guidance. I need to do things a little bit more strategically. And so we develop pull together a system of systems engineering team that has objectives, a lead manager, some people to do that engineering at the SOS level with participation from the constituents, but they don't have complete charge over the constituents yet. They have some authority, they have some funding, and so but yet they can make decisions that might be difficult for the collective to make. And then lastly, we have what we call the directed system of systems, and this is something where you have a lot of authority and a lot of responsibility at the system of systems level. There is an organization, sometimes it can be a government organization, a corporate organization, or what we call a lead system integrator that is put in charge of it, and they have contractual relationships with all of the constituent systems. And they use contracts to manage the evolution or the development of these new systems. And they have a lot of power because they pretty much control most of the funding for those constituent systems. An example of this might be the business enterprise at the hospital that has a CIO, Chief Information Officer, or Chief Technology Officer that's responsible for it and controls the funding for all the systems and all the players. Or it might be a lead system integrator like Boeing was for the future combat systems, which had a lot of problems, and they've kind of disbanded that, and they're going back to more of an acknowledged one in places, or having it managed by the government now. So this is our taxonomy. I'm going to show some examples here. And so when we look at systems engineering, we typically have a process that has phases, and we start off with an exploration phase. There's a capability that somebody needs to perform. You're going to explore what the options are. You're going to down select to a few, and you're going to do some sort of evaluation process where you're doing trade-offs on the better options and trying to select an approach out of that. Once you down select, you go into an architecting phase, a development phase, and if you're successful, you roll it out and you go into operations. So this sort of process still typically happens at the SOS level. When you'll see though how they're leaning up, and it's kind of transformed a little bit. And you have all of these systems down here going through a similar sort of process, but they're not well aligned. Okay? And this first case, System X, he's a really old system, and he's kind of what we call in sustainment or maintenance, not changing too much, brittle, fragile, don't want to change, but you've got to do some changes. So their little change packages go out, but it's pretty much in a persistent operational state. These other systems are more mature systems that are out there, but going through major upgrades continually. And then this last one is an example maybe of a new system that's coming, and it's going to have a much longer time frame that you're going to have to synchronize with. So we're starting with the most authority, most responsibility, the directed system of systems. And you can see that all of these systems report up to the system of systems level. And so there's a lot of control and ability to manage them. We're going to talk about challenges. I see you shaking your head. Yes, there's lots of challenges in there. Here's the exact same diagram sketched out for the acknowledged. And what you see is the acknowledged is looking down, observing what's happening, trying to steer it a little bit and guide it, but they don't have a lot of tight controls. Okay? And then lastly, here's our collaborative. This whole team goes away. And you just have these systems kind of out there on their own, and when it makes sense, when they have the bandwidth, the time and the resources, then they'll come together and see what they can do. But this gets very political, because each one of these systems is that they're negotiating for more dollars to come their way. They want to build their systems bigger, have more capabilities so that they can market for other systems of systems, and so on. So it's turned out that the directed systems of systems have had a lot of problems. And the reason for that is if you start looking at systems of systems in the commercial world, in the Department of Defense, you have some very key strategic systems that are part of multiple systems of systems. And trying to synchronize them across all those systems of systems, that just becomes very, very difficult. A classic example I like to use is GPS. No one single systems of systems, no one commander is going to be able to tell GPS what new functionality I need. It's going to be a coalition. They're going to decide what are the strategic ways that we're going to evolve GPS over time. And so everybody is going to have to conform to what GPS says. They're kind of like the center of that space. And so what has happened is that most of the systems of systems that we find out there today are of the acknowledged nature. They're either collaborative or acknowledged, and when they become important, they tend to put someone in charge of them to help guide them. In the Department of Defense, we did a survey of about 18 different systems of systems. There were communication systems, command and control types of systems, integrated combat systems. We had the ballistic missile defense systems in there. Intelligence information systems, the satellites that are taking the images that flow down into through the communication systems and into the command and control systems. And then space-related systems might be space radars or the space integrated pictures, assessment pictures, and so on. And as we talked to these engineering teams at the SOS level, what we realized was they were taking the traditional engineering activities that are in the old, if you're familiar with the old V model, you start with requirements and you decompose them down into a design, and then you build, and then you test, and you go on up, and then you deploy. They said, you know, we can't do all that stuff anymore, and it doesn't make sense. We're trying to manage a group of systems. So what is it that's really important for us to do? And first is we take these high-level capabilities that we need, like better defense, and we try and translate that into something that we can say, okay, we've got this group of systems, how can we improve defense? And so you translate that into a set of requirements that you can then deal with looking at your constituent systems. As these systems are implementing their own sets of changes, you have to kind of try and keep tabs on what they're doing. So understanding those systems, watching what they're doing, what their relationships are with each other, what are the communication protocols they're using, what information are they already sharing, what more information do they need to share. Related to that is assessing their current performance out in the field. How well are they performing? What are their problems? What is not working well? When a crisis happens, can we have the real-time performance that we need? So we have to understand the current systems, who they are, what they're doing, monitoring and assessing their changes, looking at their performance. Then we look at the architecture. How are they integrated today? And is that sufficient to meet the needs? Or do we need to start changing that architecture and realigning systems? So that's developing and evolving the system of systems architecture. These capability-related requirements come down here into a product backlog of sorts, and they're seeing, okay, this is the highest priority things I need to do. I'm going to allocate these requirements to different constituents, and we're going to go into a development cycle, and then we're going to orchestrate those, the upgrades to those systems to perform those requirements. And so, but what are the key challenges? Number one is focusing the constituent systems, stakeholders and engineers on the problem of the systems of systems. If they're already stretched thin and they can't even provide their own stakeholder needs, or their system is too fragile and every time they touch it, it breaks things and it breaks the system of systems, you got a problem. Then you got to coordinate the development of the new capabilities, and if you remember those development timelines are not lined up well. So you're going to have to float out a piece at a time and get the systems to be able to operate in the old environment as well as the new environment that you're moving towards. And then so that leads into creating that roadmap to guide those activities so that you can get to that target area. And then how do we test these things? Each one of those systems typically goes through a lot of rigorous testing before it gets deployed. But if the pieces aren't all together there, if they don't all come together at the same time, then you can't test that capability level ability before you have those systems deployed. So you can guess how they might operate, but you can't predict it. One of the things I think it was on one of the earlier slides I probably didn't talk about. One of the other things that we're really interested in is what we call emergent behaviors. So you can plan all these things, and you have these requirements, and you have these things that you want your system to do to contribute to the systems of systems, but once you pull it together, does it work as planned? Do the users use it as planned? And you sometimes get these emergent behaviors. Some of them can be really good. You can get much better performance than you thought, but some can be really bad. Okay, and they drop data, they lose data because things are not properly synchronized or the timing's not right between the different systems and what have you. So these are the things that you're focusing on, typically in the system of systems environment. So a little bit more about the synchronization challenges. We took those system called the core elements, and we kind of laid it out. The traditional engineers still like to see kind of something like the V model. So we kind of laid it out. And so when you initiate an SOS, you do some analysis up front to kind of establish what your baseline is for that system of systems. Then you start conducting further analysis to see how I want to start changing it. You go into the architecture, the planning for the next upgrade, and then implementing it. So you've got these systems down here that are in different states of development. Some of them you can come, if you just need them to do little changes, you can probably include that in the current upgrade. Some other systems you might have to wait for 2 or 3 cycles to get it in their product backlog so that they can implement those capabilities. And if you have a new system, it's probably going to be even longer getting out. A lot of systems today will try to have something like a 9-month to an 18-month refresh cycle where they roll out new capabilities. So if you can get into their battle rhythm early on, flow those things out there sooner than later. Sometimes you're so full that you're going to have to wait for 2 or 3 upgrades. A new system, on the other hand, may take anywhere from 3 to 5 to 10 years, depending on how large and complex it is. So this is for larger and more complex systems, as well as systems of systems, we've come to realize that there's no big bang development approach. You're never going to start with a clean sheet of paper. But rather, you're going to have these existing systems that you start with. You're going to have to determine what the single system battle rhythm is, and out of that come up with what we call a battle rhythm for the total SOS. What is the upgrade cycle given that these other systems are upgrading at a certain refresh rate? And so what you want to do is you have this agile overarching team that is looking, what are my new capabilities? What can I do now with the systems I've got? And then they'll decide on what the high priority things are, what they can accomplish. They flow that down to the development team, and you have these short, stabilized, incremental updates of the constituent systems. And at the same time, you've got continuous monitoring from the verification and validation perspective. It might be testing, it might be assessing performance of the fielded systems, and those sorts of things. And so we're moving away, we're calling it evolutionary acquisition of capabilities as opposed to a brand new big bang, I have a plan and in 5 years I'm going to have a new capability or a new system or something like that. That just doesn't seem to be doable given the pieces we have to work with and the complexity of our systems. So when we were interviewing the system of systems engineering teams in developing the DoD guidebook, we started hearing evidence of things that I would characterize as lean principles. They're taking a very holistic view of all of the constituent systems. They're looking for continuous processes to improve and enhance the capabilities that they have. They're pulling knowledge from the constituent system engineers as they need to. The system of systems engineers realized early on that they couldn't be knowledgeable in all the details about all of the systems, and so they need to collaborate with the experts on each one of those systems and pull them together and do some team building. And so it's respecting and creating trust and transparency among all the stakeholders. A lot of things, if you take Stan Settle's lean principles class, I guess some other people are teaching it now, but you hear it a lot. And so they're minimizing waste. They're not spending time on things that they can't control, that they can't, that are not value adding to the system of systems. And they're focusing on what am I currently doing? What are the future possibilities that I need to do? What are the strategies for realizing those future possibilities? And then how do I manage that change process? This whole structure has come out of the MIT Lean Advancement Initiative and a lot of the studies they're doing on lean enterprises. And so we looked at this and we said, well, how does that map up against these core elements back on what we call the trapeze chart? And we see we've got really good coverage. We've got the current understanding of the system of system, the future possibilities, strategies and tactics for the future, and then monitoring the change process with a major emphasis on stakeholders and the holistic enterprise view of the systems. And the reason you need to pay attention to that holistic thing is, what happens when you change this system or you start pushing on this to improve performance? What is that going to do to the other systems? What kinds of emergent behaviors are you going to get if you start adjusting things one at a time? And is it going to go in the direction you want, or is it going to go in the wrong direction? And so that's why current understanding and continuing to understanding and managing that change process are so important, whether it's a business enterprise or a DoD system of systems. And so we did that, and then we said, well, let's go back to, we've got some data that we can mine from those interviews. And so we went back in there and started mining it on those 18 system of systems, and we started looking across, and we found evidence that it was really overwhelming. It was pretty amazing how many of them are implementing these lean principles. They haven't, there was only one that said, oh, we're trying to be lean or integrate some lean principles into our organization. But all the rest, we're trying to do more with less and really effective in managing that system of systems. And so we're seeing a lot of that.
What's lean stand for?
What?
Is lean stand for something?
Lean? The Toyota lean principles start out with the manufacturing, how to optimize the manufacturing process.
Lean and mean.
Lean and mean, yeah.
Lean and mean.
It's not an acronym.
No, it's not an acronym.
But what is the difference with agile?
Oh, that was another paper I wrote. So Agile has some lean characteristics, but I think some of us who've studied it, Agile, depending, especially in software development, what they found is they needed something called refactoring. That if you don't have that big picture in mind and that overarching architecture, you start building things and all of a sudden you don't have the infrastructure to scale up that you need, and they have to go back and they have to rebuild. And so that was one of the major disconnects I found. They have, like I said, a lot in common, but if you run out there and just start building little pieces and hoping that they're going to come together later, sometimes you miss the mark. And so people are talking a little bit more these days, and you'll hear Barry talking, and we've been writing some papers on what we're calling architected Agile. So you build your infrastructure up front, and once you get that established and your protocols and your frameworks and everything like that, then you can go into a more traditional Agile type process and building out the details in your system of systems or your complex system. But the initial Agile works really well when you're doing really small systems and for small businesses and things like that. So I don't want to bash it too much, but you really need to think about it. So the next area of research that we're doing, and this is actually related to what my dissertation was, is how much does it take to do this? And how does cost come into the trade-off? And one of the things we also would like to do is look at schedule, but we haven't been able to pull that together yet. So we start with the system capability, and there's a system engineering cost model out there that we started with called COSISMO, Constructive Cost Model for Systems Engineering, and its size driver is a number of requirements, and we call them C-level nominal requirements. And so the concept behind this is you take a size driver that you can use to compute a nominal effort, and then you have these other cost factors or characteristics that will adjust that nominal effort up or down depending on how complex it is, how mature the team is. And those cost parameters tend to characterize the engineering processes that you use, the capabilities of the people, how well suited they are in this area, how knowledgeable they are in this area, as well as the tools. How much automation do you have, and those sorts of things. And so you take those equivalent C-level requirements and apply these other cost factors, and then you get the effort. Well, the initial cost model treated the system as a single entity, and it came in a single systems engineering team, and it came up with a single effort for that team. But in the system of systems, you've got the system of systems engineering team, you've got the engineering teams of all your constituents doing things. They all belong to different companies, different organizations, different cultures. They could be international as well as national. And so you really need to characterize them differently. And they're each going to have different pieces that they're implementing, some more complex than others. And so we looked at breaking apart COSISMO so that we could estimate the different pieces and then pull them together to understand the full system of systems engineering effort. What am I doing on time here? Pretty good, I guess. Another question that comes up, if I'm putting together a system of systems engineering team, what are the engineering artifacts I need to help this process? What do I need from the management perspective? What do I need from the technical perspective? And we've kind of called these the engineering artifacts. And what we found is, again, they're being lean and not developing all the traditional documentation unless it's value adding. And what makes it value adding is what helps me communicate information between the system of systems engineering team, the constituent systems, and the stakeholders of all these constituent systems, as well as the end users. And there's something that, I don't know if you're familiar with boundary objects. These are objects that have potentially multiple views to characterize something of interest. And so what we found is that most of these artifacts that the system of systems engineering teams are developing fall in this category of really key boundary objects that they need to use to manage the evolution of the system of systems. The other thing that's when you look at the theory behind boundary objects, Most of them, people think of models, of prototypes, of documents, and things like that. But you can also have a person be a boundary object. And this is the person that has the vision in his head or her head of what the total system does. And sometimes that's really hard to capture in a model or a piece of paper or something like that. And so you have to identify these people that are performing as boundary objects in your organization, because if you lose them, you're going to really be lost.
I don't think we are familiar with the term boundary object. Could you, again, because I don't think there are many system engineers in the room, could you just add?
This actually came from organizational theory.
Okay, so what is really the boundary object?
So a boundary object is it's a thing. It could be a model. It could be a prototype of something. It could be a document. It could be a set of requirements. It could be a design. It could be an architecture. It could be a management plan that helps guide the activities of the different groups. And there's, I can give you some papers, and Anne Marshak, I forget what, I think she's in the organizational group. She's done a lot of work and research in this area. And what is key to these is, like, for instance, take the architecture. Stakeholders want one view that's very simple because they're not the techies. And so their view of the boundary object is the simplified high-level version, whereas the technical engineers, they want to go 10 levels down to figure out where all the bits are going and where the power supplies are and how the power supply is getting their continual refreshes and things like that. So that boundary object will have many views for the different types of people. But it's all, you need to keep it consistent at whatever level, at all those levels, so everybody's looking at the same thing, the same pieces of information, just different views.
It's similar to output, basically. Maybe some kind of what comes out of the system.
Yeah, they're things that get developed. Okay, and we talk about how much value the different boundary objects have, whether they have a short life or a long life in the development cycle. Certain things, you'll put together a plan, and once you've got that increment done, that plan's out the window, and you're planning the next upgrade. So they'll have a real short life. Whereas the architecture, you're going to continue to evolve over time, and it will stay there for the duration of the system development cycle. Is that clear? Okay, and the last area I was going to talk about is testing. As I mentioned earlier, the different pieces of a system capability get rolled out at different points in time. And it's probably all going to be fielded. And what are you going to do if it's not working right? And how you can't test it before all the pieces are together, but no one's constituent system is going to hold up their upgrades waiting for the rest of the SOS to catch up. They have their own needs they need to go out and deploy, and they're not going to sit there and wait for 2 years until everybody comes together. So what the system engineering teams are doing is putting together the test team in a framework. If there's models and simulations to help them in the testing, they'll use that so they can test a little. They're going to build on the constituent level testing, and if possible, maybe insert some of their system level tests into those single system tests to help get a better understanding before it's deployed. But what they're really going to end up doing is there's going to be a test range or an operational testing environment, limited deployment of that system of systems. If you're in the hospital, what we used to do on the healthcare systems is we would choose one hospital in the network, and we would take the old system down on the weekend, bring up the new one, and we'd start running with it Monday morning. And you would go so far, and then you have your go, no go decision as to, I have to back out some changes, it's not ready to go yet. And so these are some of the things that you can do for the system of systems. It's risk-based, it's evidence-based, you know, what can I see based on my mission scenarios, and it's focusing on, it's not going to test the systems in totality, but focus on the system of systems capability, the network, that's pulling them all together, the interoperability of them, how are my data standards, is the data going at the right rate, is it in the right formats, is it making sense when it transitions from one system to another, and what are the emergent behaviors that I'm finding, and are they okay? that's what the initial test will focus on. And then what you do is you continue to monitor how the system performs over time on a daily, weekly, whatever basis. You've built in some metrics that get reported out, and it will tell you how well it's performing. And then you take feedback from those things and field it into the next set of changes. If it's not performing quite as you want, you'll adjust, you'll tweak a little bit for the next iteration. And so here comes the fun part that we've been working on with our Ensayo model. It's a regional area crisis response system of systems. And I think most of the people in Southern California can relate to this one really well. I'm from San Diego, and we've had the Cedar fires and the Witch Creek fires and things like that. This last year, you all had more of the fires. And as a result of these things, and things such as the Katrina hurricanes, we've realized that we need to pull together regional assets really quickly to respond to these crisis situations, whether it's an earthquake, whether it's fires, whether it's a hurricane, whether it's a hazardous material spill on Freeway 5 at rush hour. These are different things that sometimes happen, and they affect all of us. So as the first responders, how can we get together, get a better picture of the situation, and know how to respond, what to do next, to minimize the impacts of the situation, save lives, save other assets, resources, homes, buildings, what have you. So this is just a sample one that we put together based on things that we've seen in Southern California, but we're not attributing it to either Los Angeles or San Diego or Orange County or anything like that, but it's kind of a composite, and now we're just playing with it and pushing to see kind of what happens. So up here we have the satellites system from above. It's a federal resource that sometimes you can use to get views of how widespread is this fire, where is it going next. We got the fire department that typically operates on its own, may have paramedics as part of them or not. The police and the sheriff's department, we may have people on the ground with handheld radios. This is what we call an unmanned ground vehicle. They're using them a lot over in the Middle East to get rid of the IADs, so you can remotely control them and go out there and do stuff. You can use these in the fire situation to go clear brush and set backfires and things like that without putting the firemen in harm's way. Here's a hazmat person. Sometimes these robotics are used in hazmat situations, go in and get with sensors and get materials to analyze. This is the planning and land use. You can have it at the city level, the county level. These organizations often keep information about the various utilities in the area, where are the power lines, where are the water lines, where are the sewer lines. They've got building plans for the big buildings, and in the counties sometimes they have building plans for some of the houses. And so if something happens in a big high-rise and you need the building plans, if you could tap into their facilities, you might get information that you need to make decisions. Here's a command and control center. You usually have somebody, it's 911 is there, and how do you, the dispatch for the fire departments and the police departments. Here we've got some aerial tankers that can sometimes come down. They can be national assets or international assets. San Diego's been using air tankers from Canada. Up here we got the news reporters. They're getting in their helicopters and they're trying to get the best picture. Well, guess what? Maybe the man on the ground it could really help him assess a situation, because they're much lower to the ground than the satellite. And if we can get a direct feed from them and pull them into our system of systems, that could be useful. And then we've got the unmanned aerial vehicles or drones that can fly over. Now, in our fictional area, the community got upset with the looters coming in, and so they were using these to kind of monitor for the looters, and that wasn't slowing the looters down. So what they've decided is, in some cases, what they're going to do is they're going to have some that they can actually arm, and we're just going to go in and we're going to take out the looters. This wakes up people at conferences when we start talking about the fire chain. So you see, you have systems that will tend to operate on their own. They could go in and handle a variety of situations. Which components you pull is going to depend on the crisis of the moment. These next couple of slides, kind of what I just went over. So our RACRS, basically, as I said, to minimize impacts in area crises, contain potential losses. some of the cross-cutting things that they want to do is identify and classify the type of process, alert the appropriate organizations, evacuate the public if necessary. That's where we have reverse 911 that kicks in sometimes. Identify and manage those needed resources. And then if it's escalating, go outside the region and start getting support from other agencies at the state and federal level or other regional areas, like San Diego sends up fire people to the LA area recently. And I talked about the strategic partnership with other commercial entities. And then likewise, yeah, supporting other regional activities.
Excuse me, a quick question.
Yeah.
If I may. Where is all this coordinated? Surely there are all this system, let's say in the case of a crisis, but where is all the decisions being made? I mean, or is it the director?
So what we have, okay, well, there are. It turns out this was what we would call a collaborative system of systems. When it first started, I'll go back to the San Diego example because I was actually working with the county at the time. This was coming together. And the fire department, the police department, and the 911 group at the command and control center were already looking at being a lot more interoperable, and so that they could share information and get things out. And when the fires happened and we had to bring in the National Guard and they didn't have communications channels that were compatible and things like that, we said we need to plan this better. And so they put a county organization in charge of it to help make this happen. And so that they're better integrated and come together quickly, establish who's there, who's doing what, instead of, oh my gosh, what do I do next? And so that's where it's been evolving over quite a few years. And what I can tell from news reports is these things are also happening in other communities.
So this is at the county level, not at the city level?
This was in. It could be at the city level, it could be at the county level, it could be at the state level, it could be at the federal level. FEMA was kind of in charge in Katrina, worked some areas better than others, but they ended up bringing in the Bureau of Land Management because they know how to fight fires and they know how to get the logistics and support the firefight, or not. The Bureau of Land Management, yes, mostly focuses on fires, but they knew how to get the food companies in there, the people to throw up the tents for the people that are working, because there's no infrastructure, and you have to, if you're going to get first responders in there. When the space shuttle went down, again, they brought in Bureau of Land Management people because they know how to get people there who can do the search and recovery, and they can set up the tent cities and everything to house them and keep them going in the areas where they needed to be. So this can happen at lots of levels. We're building a model. We're working on this with MIT and some other people who are looking at systems of systems, and we're trying to develop a model and some case studies so that when we look at things, we can say, well, how does this play out in these different scenarios? And it kind of helps us to engage people that are working these at the city and the county and state levels and things like that.
Do you actually play games in a sense,
well,
scenarios, and then see how the systems interact?
We're thinking about getting it to that point. We're trying to get some graduate students and help us build this up a little bit more. Right now, we're using the Systems Unified Modeling Language just to kind of characterize it and come up with the attributes. What's really interesting in our studies is most of the problems are at the interface levels. And the compatibility of the data maintained by each one of these entities. If the data standards aren't right, you can't mesh it. You got to go through too many conversions, and then there's a high overhead to communicating information because you're converting for 10 different ways. When I was working with the GIS system for this internet service provider, we had like 40 commercial products that we were using in the back office systems, all the way from the network managing to the HR to the call center to the billing system. We just took one thing, customer address. Out of 40 products, we had about 30 different formats. And so, you know, think of each of these systems. They all want to respond to the same address, but can you pull it from a single repository and broadcast it in one format, Or do you have to do all these data conversions and things like that? And so there's a lot of work in characterizing, and we're finding the engineering tools that can help us characterize these interfaces, both with respect to data types and the timing and accuracy of the data, the precision of the data, are really pretty valuable. So we also use this, the system of systems when we go out and do tutorials with respect to incremental commitment model or system of systems engineering types of tutorials. And so we look at getting people to focus on one or two of these RISC different teams and to come up with strategies on how they're going to do it. And again, the incompatible interfaces between the existing systems and the COTS products and how interconnected you can have them. What are the scalability issues? Things work fine when you have 10 users. What happens when you have 300 users? What happens when you have 1,000 users trying to communicate? And so maybe some of the organizations have ongoing projects to integrate. Can you tap into that? Can you leverage that? Or are you going to have to get them to back out because it's not going to scale up for everybody else? There's always limited budgets. At the state and federal level, you're very seldom going to get any of them to change for a single county or a city or a region. They're going to look more holistically, so you're going to probably have to align yourself with them. It's kind of like my GPS example. There's a lot of federal funds coming out there that if you can get your act together and jump on it quickly, you might get some funding and be able to take it to the next level. But then you still got to go get your local politicians, your county board of supervisors, and the city council to agree to all these things. And we know what happens as you start going from the city to the county to the state levels and how fast you can get politicians to move. We've got citizen privacy and security issues when you start opening up all of these systems. What's going to happen to their privacy information, and are people going to know too much about the layout of their homes and what's in their area and those sorts of things. And then you've got, when a real crisis happens, the overlapping authorities. So when Katrina happens, first New Orleans starts taking over, and then the state jumps in, and then the feds jump in. And how do you make those transitions as the crisis starts escalating? So you look at what your risks, issues, constraints are, and start trying to set up a framework there, and then you start looking at what your desired long-term characteristics are and what you need to do. And out of this, in the interest of time, you can read it on your own, but out of this you end up figuring out, well, I want to do this, I want to do that, and you start building a backlog of all these capabilities you want to support. Well, you know you're not going to have money to do it all, but what you need to do is prioritize them. What's most important, and how can I do this, and if I have this much money, that's where I can start working and set up that battle rhythm to evolve my system of systems. So that kind of summarizes there. We're continuing to do research in this area. All of these things are coming into play. We've got the lean lens analysis, and that seems to be informing a lot of these things as we look at the lean characteristics and how they're choosing to lean up their engineering activities and move forward and upgrade their the systems of systems. Cost modeling is really important, but what we realize is there's lots of organizations, and so they're wanting to users are wanting them grouped in different areas. First there's the planning, then there's the implementation, and then there's the testing areas. And there's an MIT group that's, actually USC is on their team and looking at system of systems level testing. And so that pretty much wraps up my systems of systems talk. Questions?
Questions for Johan? So any question for Johan?
The defense DoD system, a lot of them are classified. And university work non-classified. How do you mix with?
Well, I didn't put that in my bio, but I worked in industry for for about 25 years before I came back into academia. And so I did have security clearances, but I no longer have one. And I can still go out and talk to these people. We can keep it at an unclassified level and still learn all of this stuff. We don't know the details of their data and things like that. But, you know, classified, proprietary, classified at the DoD level, at the government level, at the city level, county level, it's all out there. But without going into those details, we can still do a lot of work. Yeah.
Yes. So you have different types of systems. How do you evaluate the different performance level to have a common, to be a standardized metrics that how do you optimize the overall system, basically?
I think your question is different systems are going to have different performance characteristics.
Yes.
And they, you know, I call it throughput or timing or precision of their data. What is the time, you know, do they update data every sub-second? Do they do it every 10 seconds? Do they do it every 10 minutes? And so you need to figure this all in, and that's where we're modeling. We're using modeling techniques to help people identify what the disconnects are. And you have to deal with it.
I'm not talking so much talking about the disconnect. It's about how do you optimize. Like you said, like you had to prioritize which system to upgrade and so on. But if you don't know the importance of that system for the entire overall systems, how do you know which system to upgrade first? You
don't get to choose which system to upgrade first.
No, I'm just talking about performance level.
Yeah.
But in terms of upgrading performance.
So when you decide to upgrade performance, sometimes there's not a whole lot you can do, and you're going to need a whole replacement system, and that's going to take you into the 5-year timeline to do a whole new system. Sometimes the architecture is just too fragile, and you're not going to be able to increase throughput or timing or anything like that. And so you pick and choose, and you sometimes choose a non-optimal system to implement a certain capability just because they can do it, and they have the engineers to do it now. And that's not the place you would typically choose to do it, but it will get my capability out there faster and more reliably. And so you do a lot of trades. You open up that box of options a lot, and you really need to do that.
Any more questions for John?
Yeah.
What is the level of control that the command center has over the systems? Like, is it just for connectivity and collaboration, or maybe on policy making?
Well, the example I had here at a command and control center, and most counties might have one that are just in charge of the local fire department, police department, 911 sorts of things. When the crisis happens, their authority escalates. And you maybe get other people in the county stepping in, the mayor, or you get the governor stepping in and putting people in charge. So the authority and who's in charge and what they can do, it changes in response to what we call the mission or the need. And typically, I mean, there's some systems that have a command and control center going all the time. Like I said, the fire department, the police department in the example. But others operate without a command and control center. They're just tools and single systems that do their own thing. But then they need to have agreements in place so that when a crisis comes, that they can tap in, integrate, join the collective, as we say, to handle the situation.
Okay, well, let us thank our speaker. Thank you very much.